if you compare this to what you had to do on the homework, I would say that this one that we just looked at on the warm-up is like a more difficult version of 45, 46, and 48. So if you could do this one, 45, 46, and 48 are a little bit easier because they're also composed of all straight lines and there are fewer different sections. 47 is tougher because 47 the graph is curved. And doing the derivative of a curvy thing is more difficult. So we'll talk about that as well. So if you were going to graph this thing's derivative, remember that derivatives are slopes. Out here on the left, what might throw you off is that the arrow is pointing up. And so you might think, oh, it's going up, so it's a positive slope. But you always reach from the left to the right. So you start over here, and then you come this way. And as you come this way, the line is going down. And so this is a negative slope, and it's going down at a rate of -1/1. So that's a slope of -1. So you would come over here and do a slope at a height of -1 until you get to x equals 0. Because then at x equals 0, this graph suddenly turns, and now the slope of this next section is a slope of 0. So because this next section has a slope of 0, over here, your derivative will be at a height of 0 from x equals 0 until x equals 2, where you have your next turning point. So I was just darking the x-axis there to indicate that your derivative is at a height of 0. And then you have another turning point at x equals 2, and now you're going up at a rate of up 2/1. So now your slope is +2. So you would jump up to a height of +2 from 2 until 3. And then you're coming back down at a slope of -2. So you'd be down here from 3 to 4 at a height of -2. And then finally, has one more turn. Now it's flat again, way out here on the right. So this guy's slope is 0. So you're going to have a height of 0 on the derivative out to the right. So that's going to be what your derivative graph looks like. This is f prime. And so that's the goal for things like 45 through 48. And I think there were like 39 to 42 was similar, but matching, where they had like 4 graphs of f, and then you had to match it up to the correct f prime option. Get out your homework. And I just went ahead and assumed that we're going to want to see 45 to 48. Is there anything else that you guys are going to want to look at besides those? $76. Okay, yes, that's not surprising either. All right, so 76. We had f of x equals, what was it, x cubed plus 6x. And we were looking at c equals 2, and we wanted to find then f prime of 2 using the alternate form of the derivative, right? So it's going to be set up like this. Anything else? Oh, yeah. Well, as soon as I find the remote. Anything else besides those 4 graphs and then 76? 54? Yeah. Yeah, the answer key copied down the problem wrong out of the book for 54, I think. Or maybe for 55. One of those was copied down out of the book wrong. So for 54, they're giving you this limit is that what? Delta x approaches 0. And is it -2 plus delta x cubed plus 8 over h, or delta x. And we want to find out what's the function that's being differentiated by this limit and at what x value, what's the c, right? And then 53 and 55 were the same prompt with different limits. Anything else we want to look at? Okay. Who wants a board point? Tamika, Ahmed, and there was a clean slate for board points. Everybody's back at 0 board points for the new quarter, except for the people who already have board points this quarter. Narose, go ahead. Anybody else who wants a board point, go ahead. George, go for it.
Are we allowed to do the ones on top?
Yeah, absolutely. Yeah, all those ones over there, the ones that are asking for the graph of f prime given the graph of f, those are fair game as well. That's why I put them up there.
You didn't do it. No. You can do it.
That's fine. You want to do, another one of those? Yeah, sure. If nobody else wants those other things, go for it. Which one were you going to do? George, were you going to do 48?
Yes.
Okay, George, do 48. Risa, do 47 if you want.
No,
Never mind. Akshay's doing 47. Has anybody done 45? Okay. Sorry, other people came up there. Preference is given to people who haven't done one yet, so they finally stepped up just in time. We got Tanika and Risa. And who is 45? Thank you, Ahmed. And who is 46? Rose. And Akshay. And George. And the rest of you can look over here at the next set of notes. As we start to look at differentiation shortcuts so we don't have to drag ourselves through these little processes. All right, so 45. Ahmed, talk to us. All right, so you look at this line and you say, what did you know about this line? Slope is 1, because you're going up 1 or up 4 and over 4, so the slope is 1. So how did you draw your derivative? At a height of 1. And it's always at a height of 1, because what's the slope of this line? Well, always 1. There you go. Any questions with 45? 46, the rows. Yep. That's it. So the derivative of a constant function is always 0. The derivative of some line function is always a constant. Now things get a little tougher with the parabola. Akshay, talk to us.
And as the line is supposed to be 4, it becomes negative. And once it reaches the x-axis, and then it becomes positive as it goes up.
So right at x equals 4, what's the slope? 0. Because right there, the curve is flat. And so way out on the left, what's the steepness of the curve? What direction is the curve going? It's going which direction? Down. And is it going down fast or slow? Fast. So we have a big negative slope. So your derivative is big negative number, way down here below the x-axis. And then as you come to the right, the slope is still negative, but it's getting less and less negative. So the derivative is getting less and less negative. It's getting closer to the x-axis, but it's still below the x-axis. Then at x equals 4, the curve is flat, so the slope is 0. So the derivative is at a height of 0 when x is 4. And then to the right of x equals 4, now the slope is a little bit positive, so your derivative is a little bit above the x-axis. And as you move further to the right, the slope gets more and more steep positively, so you're going up at a faster and faster rate, and so the derivative gets higher and higher and higher above the x-axis. So graphing the derivative from a curvy f is a little tougher because in this case, the slope is always changing as opposed to the slope being some constant value. And then 48 was George. Yep.
-1, like I'm -1.
And then
Then for the slope of 1, I want 1.
now 47 and 48 are kind of similar. Like both of them, you're going down negative slope, you get to x equals 4, and then you have a positive slope to the right of 4. The main difference is what's going on right at x equals 4. Why are the graphs of f prime different for these two curves when they both kind of have negative slope, changing direction at 4, and then positive slope? What's different about x equals 4 for these two things? Yeah, we got a sharp point. We have a sharp, abrupt turn there in the absolute value. So here, the slope is always -1, and then it's always +1. There's no gradual shift. Over here with 47, there's a gradual change from negative to positive slope because of the smooth curviness of the parabola. So that's what accounts for the difference in the derivative graphs. Oh, that's a good point. Yeah. Dev's saying, hey, all this stuff is great, but where should the jump in the derivative happen? At x equals 4, because at x equals 4 is when we stop going down and start going up. I should have noticed that. So we should take this thing and move it all over to when x equals 4, because at x equals 4 is where the change in direction happens. So you got to pay attention to where do things happen in terms of like the x location, and that's where you have the jump, or that's where you have the slope equals 0, for example. Risa, talk to us. No, you're not Risa. There you are. Talk to us about 54. So this is C plus H, right? What's being done to it? And then if you're ever lacking confidence in these selections, you can check by plugging -2 or whatever your C value is into the function and see if you get that number here. So what's -2 cubed? -8. And if you minus -8, you get a +8 there. So it works out. So you can always check your selection by taking the C value that you think is correct, plugging it into the function that you think is correct, and if you get the second half of the numerator when you subtract, then you're good. Tanika, talk to us. There you are.
So I just started substituting, and f of x is just the function, so it's x cubed plus 6x. And then f of 2, I just substituted 2 for each x. So 2 cubed plus 6 times 2. And then I started evaluating it out, and so it's x cubed plus 6x minus 8 and minus 12 because of the negatives. And 8 and 12 is equals -20. And then I factored those out. I figured that I just assumed that x -2 was going to be canceled out. So I tried to look for just factor it out like that. I got x squared plus 2x plus 10.
How did you get this second part? So I understand like we have x minus 2 in the denominator, so let's just assume that x minus 2 is a factor. How do you then get the other factor then?
Okay, so I was struggling with trying to find that, so I just put it in the calculator, and it was like, that's the thing. So I was like, okay.
The calculator does that for you?
It was like the one on the online ones.
Oh,
Yeah.
okay. So let's see how do we do that. So like it's reasonable to assume that x minus 2 is going to be a factor because you see x minus 2 in the denominator and you know I need to kill this x minus 2. The only way that happens is if x minus 2 is a factor of the numerator. So that's a good assumption. Then how do you find out the other factor? Synthetic division. So remember synthetic division? You take the coefficients of this thing and then you do this up big L thing. So x minus 2, if you solve this, x would equal 2. So that goes outside your big L. then these guys' coefficients go inside the top of your big L. So you have a 1x to the third, and then you have a 0 for the x squared. Don't forget that. Then you have a 6 for the x, and you have a negative 20 for your constant. And then what's our process for synthetic division? Take this number, the first number on the inside of the L, and you add it straight down. What does he have to add to? Nothing. So he adds all the way down, and you have 1 still. And then once you have a number down here, what happens to it? Multiply by 2, and you go up into the next column. So add straight down, multiply by 2. Add straight down, multiply by 2. Add straight down, multiply by 2. Add straight down and hope for a 0. If the remainder is 0, ta-da, x minus 2 really is a factor. That checks out. This stuff gives you your constant x and x squared coefficients. So you have a 1x squared, a 2x, and a 10. And they're all positive, so pluses. So that's where she's coming up with this. So like x minus 2, I understand why we want that to be a factor, because we have an x minus 2 in the denominator that needs to die. So assume that you're factoring out an x minus 2, and then to see the other factor that results from it, do synthetic division with the original polynomial that you're trying to factor and x minus 2, and there's your synthetic division process. So one of those random one-off topics in Algebra 2 from like 2 years ago that you learned, and it was like, that's easy. And because it was really easy to learn, it was really easy to forget because it required very little thought to really ingrain in you, so it didn't get ingrained. So the nice thing about it is that it's easy to bring it back. So that's where that comes from. And then she's like, all right, cool, yeah, x minus 2 does work. It cancels out. X squared plus 2x plus 10 is left over. Now take your limit, and you won't get division by 0. Instead, you get 18. There's your derivative. Good news for us, we're going to start shortcuts today so that in practice, when we see this limit, you're going to say, I don't need to do the limit anymore. I'm going to use the shortcuts because I know that limit means a derivative. And I'm going to figure out what I'm differentiating and then use the appropriate shortcut. Questions before we move on? All right, dice. I'm rolling 4 dice, so I'm going to collect what they tell me to collect instead of what not to collect. So I'm rolling a 3, a 3, a 4, and a 3. So 3 and 4. So row 3, row 4, and that's it. All right, cool. Oof. All right, so far in this quarter, we've collected rows 1, 2, 3, 4, and 5 so far. So everybody except Prince. All right, notes. Let's start looking at shortcuts. We're going to start with what's called the power rule. These are what we call basic differentiation rules. And all these different rules, you need to remember, these are shortcuts to avoid the limit process we've been doing for the last week. So our basic differentiation rules, the main one is the power rule, for taking the derivative of x to some power. And then you've got some others that are fairly related, actually. So, power rule. If you have x to some exponent, x to the 5, and you want to take its derivative. So when you see this d over dx, that means the derivative of that thing inside the brackets. So if you have the derivative to take of x to the n, all you do is take the exponent that you see, dump them down in front, and then reduce the exponent by 1. So if you're taking the derivative of x to the 5th, you don't need to worry about x plus h all to the 5th power and distribute that out. Thank God. You just need to do 5 times x to the 4th. Boom. Done. Or if you have the derivative to do of x to the 3/2, this works with fraction exponents. Dump the 3/2 in front. Now it's 3/2 times x to the 1/2, because 3/2 minus 1 is a half. Or it works with negative exponents. If you have the derivative to do of x to the -2nd,
Negative 2 times x to the negative third. Just make sure you subtract 1 correctly. So that's your power rule. Yay! And there's an explanation of what's going on. So whatever the exponent is, it gets multiplied down in front. And if there's a coefficient there on the x, if it's like 5x to the third, 3 multiplies down in front to the 5. And now you have 15 out front, and then x to the second. So once you've multiplied the exponent that you see down in front, you just reduce the exponent by 1, and you're done. That's your power rule. Now, kind of in line with the power rule, we have the constant and linear rules. The derivative of a constant is 0. And it makes sense. We looked at 46 on the graph. The graph of 46 is a constant function. Y is always negative 4. And the derivative of a constant function was the slope of 0. So that makes sense. And you can also think of it like, what's the exponent on the x here? Trick question. There is no x. So how many x's do you have? 0. So x to the 0, if you do your power rule, you have 0 times, who cares? 0 kills it. So derivative is 0. And then the linear rule is the derivative of a linear function is just its slope, which is the coefficient. So derivative of x is 1. Derivative of 2x is 2. And that ties back into the power rule. If you have x to the first, that's what this is. Multiply the exponent 1 down in front. And then you have x to the 0 that just disappears the x, and you just have 1 times whatever coefficient was there. So these two things are just kind of like corollaries of the power rule. Notice the power rule has 3 exclamation points. Know that. That's like the basis for all other differentiation rules that we learn. So later on in this chapter in 2.3, we'll learn what's called the product rule and the chain rule. And those rely on the power rule. And then in 2.4, we'll talk about, no, I didn't say product rule and chain rule. I lied. Product rule and quotient rule. 2.4 is the chain rule. That also relies on the power rule. In 2.5, we'll talk about what's called implicit differentiation for when you're dealing with something that's not even a function. And that also comes back to the power rule. So all these shortcuts for differentiation come back to the power rule. So we got to be comfortable with this. And then these other rules are just kind of like more generic. If you have 2 functions and they're being added or subtracted, and you want to differentiate the whole item, you can differentiate each of the 2 functions separately and then add or subtract their derivatives. So you don't need to like figure out, hey, what's the new thing that I get when I combine these 2 functions together? Just differentiate the 2 functions separately and then add or subtract the derivatives together. And if you have some function getting multiplied by a constant, you don't need to figure out like, hey, what if I distribute through the constant? Just differentiate the function itself and then multiply that by the constant, and you're good. So that's your basic differentiation rules. And what we're going to do then is work through examples and make sure we can kind of get comfortable with it. And then, because this is going to take us so much less time to actually get the derivatives, we'll then also like start to do stuff with them. Probably not today, but certainly by the end of the week. We'll see, okay, how can we use the derivative to like create a tangent line equation more easily, or to like start to think about word problems, see how does this apply to like throwing freshmen out of windows or something. So stuff like that. Questions with any of the rules? All right, make sure you have them while I start putting up some examples here. Do you guys prefer notes written out like this or notes on the overhead? Or do you not really care at all? So show of hands. Who votes this way? Who votes the overhead? Who votes out? Okay. That's certainly the most convenient, but I prefer this.
Does anybody need more time with the notes?
Yeah. I mean, we'll see. I'm handing these things out now so that they're already out by the time we're ready to jump over them. I need two more.
Anybody still need more time with notes? All right. So, what's the derivative of y equals 3? And what should we call it? Y prime. You could also call it dy over dx. Why won't we call it f prime of x? Because that wasn't called f. So you're only going to use function notation f prime of x if the original function was called f of x. If you're given g of x, you'll use g prime of x. If you're given y, you'll use y prime or dy over dx, which we pronounce dy dx. I don't know why. All right, this next one. What's the derivative of pi squared? Is it 2 pi? Well, what is pi? Is pi a variable? What is pi? It's 3.14. What do we call that? A constant. It's a number. So what's the derivative of pi squared? Really? 0. Because if pi is a number, guess what pi squared is? Just a bigger number. So pi squared, it's about 10. So the derivative of that is still 0. So don't be fooled by seeing an exponent and automatically thinking, oh, power rule, only relevant if the exponent is on a variable. If you don't have a variable involved, then this thing is a constant, no matter what it looks like. We can make this great big ugly. We could say this is 1/3 pi squared all over e. All of those things are just constants. 1/3 is a constant, pi is a constant, so when you square it, it's still a constant. E is just a number too. It's like pi, it's weird. But it's just a number. So all of this is just a big ugly number. So when you differentiate it, you're just going to get 0. Here, do we have a variable? Yes, what's our variable? All right, we have a variable this time. It's r, so we can use our power rule. Did anybody recognize what is this equation? The formula? Close. Volume of the sphere. When we differentiate it, we'll get surface area of the sphere. All right, so when we do our power rule, what happens? Well, we take the exponent, and what does the exponent do? Times down in front to the coefficient. What's 4/3 times 3? 4. Pi is also there, getting multiplied, so it's 4 pi. And now what's your new exponent? 2. You reduce the exponent by 1. 3 minus 1 is usually 2. We call that v prime of r. And if you recognize that that's the volume of a sphere, it turns out that thing, the derivative, is the surface area of the sphere. The same relationship exists between circle area and circle circumference. The circumference is just the derivative of the area. I don't think it works for other shapes. I think it's just circles and spheres. Any questions with 1? 2, f prime of x, whiteboard time. So, basic power rule, f of x equals 4x to the third. What's f prime of x, please? Write it down, hold it up. And you guys are forgetting something. Thank you for labeling it, Andres. Good, 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 good. Arnor, did I hear an audible eye roll? Yes, yes, yes. Yes, yes, yes. Nope. Yes. So the exponent does not replace the variable. The variable is x, that doesn't disappear. And I'm not finding the derivative at a particular point. So you multiply the 3 down in front to the coefficient. 3 times 4 is 12. There's your new coefficient. The x is still x. You reduce the exponent by 1. Now it's x squared. Always label your derivative and always label the given function because labels are important. No. 3 times 4x squared is not the same as, you know what? No, it's not the same. Because here, what's getting squared? The 4 and the x. 4 squared is 16 times 3 is 48. So, don't overcomplicate it. The exponent multiplies the coefficient. There's your new coefficient. Reduce the exponent by 1. Same thing happened over here. The exponent, 3, multiplied the coefficient, 4/3 pi. 3 times 4/3 pi is 4 pi. There's your new coefficient. Reduce the exponent by 1. You don't need to break out parentheses here. Not yet. Now this next one, you look at this and say, hey, wait, whoa. How am I going to do power rule if I don't have an exponent? So this is where power rule gets a little interesting. You sometimes need to rewrite the function so that it fits your power rule pattern. What's x square rooted the same as? X to the 1/2. Now do your power rule. All right, good. Thank you for then getting rid of the negative exponent. No, wait, no, you didn't. Now please get rid of the negative exponent. Don't use your equal sign. Hey, thanks for simplifying it all the way. There you go. So you'll notice that when you reduce the exponent, you get a negative exponent. And what's our opinion of negative exponents? They're bad. We don't like negative exponents because we're number bigots. So we're going to throw x down the stairs, because that's what bigoted people do. And we're going to make the exponent positive. So we multiply the 1/2 in front. So I have 1/2 x to the negative 1/2. That's what you get when you subtract the exponent by 1. And then you're like, I don't like you, you negative exponent. So you throw the x down the stairs to join the 2 in the denominator of your fraction. And then if you're really feeling up for it, you can turn it back into square root notation. And that's 2 square root of x. And don't forget your labels. That's g. Is that a board point? Well, would I take off a point for that on a test? Yeah, probably. So, yeah, that can be a board point. Who was it? Zelda? Thank you, Zelda. So, if you have a negative exponent on the back end, like you take a derivative, great, and you have a negative exponent, throw that thing down the stairs, show them who's boss, yank that exponent positive, and that's how it should look like. And then if you like have x to the 1/2 and you don't like fraction exponents, turn it back into radical form. If you don't mind radical form because you're just an open-minded person like that, or if you don't mind fraction exponents, you can leave it like that. I don't care, whatever makes you happy. Who? Ah, damn it. Grace, you're welcome. I was so confused in what was happening because you used the wrong letter. Okay, so sometimes in order to make power rule fit, you need to rewrite the function into like power form so that instead of a radical, it's a power. Same thing here. So the temptation with this is to say, oh, I have an x to the third. I'll do power rule downstairs, and I'll have 5 over 3x squared. No. So instead, you have to rewrite that as well. The x has to be in the numerator before you do your power rule. So if x is in the denominator, you can't do power rule right now. You need to rewrite the function. So rewrite the function. Now when we rewrite the function, what is the label? Is it h or h prime? It's still h because we haven't differentiated. Only break out the prime when you actually go to do a derivative. So when you rewrite the original function, it's still h. You haven't taken a derivative. You're just taking what you have and giving it a facelift. So this is the same as 5 times x to the what? -3. So here, in order to be able to do the derivative, you need to rewrite it with a negative exponent. So negative exponents, they have their uses. We'll give credit where it's due. Now you can take your derivative, and you get h prime of x equals what? -15, and then x to the -4. Remember, you reduce the exponent by 1. So -3 minus 1 is not -2. Every year I have somebody say, oh, it's -15x to the -2. You don't know how to add or subtract negative numbers. So subtract the exponent by 1. Now you're at -4. And then, are we done? No, because we're hateful people. We don't like negative exponents. Throw that thing down the stairs. What does this look like at the end? -15 over x to the 4th. So only the x goes into the denominator because only the x has a negative exponent. The 15 is just a negative coefficient. Those are allowed. We just don't like negative exponents. So instead of multiplying the 15 by x, we divide the 15 by x, and now it has a positive exponent. Any questions with D, E, F? All right, for this next one, now we're seeing, oh my goodness, it's so much easier to use the power rule than to use that limit process because look at how fast it is to get the derivative. We didn't even have to do the whole limit thing. So much quicker, and now you can find the derivatives of much uglier functions than what we've looked at so far. Can you imagine doing this 5 over x cubed with the power of the limit process? That would suck, because you'd have to do x plus h all cubed, and you'd have to deal with like the fractions inside of a fraction business. Ugh. All right, and then you get to plug in different numbers to your derivative to find the slope at different points. Super easy. Right now, first off, find the derivative of f of x equals 2x to the 4th. So we'll break this down into little chunks. Please write a little bigger. I know I went right here, but come on. You have this whole board and you write it. Label it. That's good. That's good. Ryan, did you forget a label? Is that why I went right back down? Don't forget your equal sign. That's good. That's good. That's good. Now don't erase it because you're going to now use it. Thank you. Thank you. And now you have a whole bunch of stuff. That's good. That's good. That's good. That's good. I was only checking off your derivative. I didn't look at the rest. That's good. You're jumping the gun. Just the derivative of f of x. We'll find out that thing next. How do you get 6? What's 2 times 4 do? It's not 6 on Wednesdays. He's telling me that 2 times 4 is 6. Okay. So, once you got your derivative, then tell me, you're missing something. You're missing a kind of important little detail. Look, read it out to me. A cubed. What are you missing?
Oh.
Okay, nice. Yeah, you need the variable still. Now that you've got that, do A, find out the slope of the curve at x equals 1. Yeah. And then use that to write the equation of the tangent line. Now, before you can write the equation of the tangent line, you'll have an x value, you have a slope. What else will you also need? A y value, because your tangent line needs a whole point, not just an x. So remember, for a tangent line, you need a slope, that's your derivative,
and you need a point of tangency. And a point of tangency involves an x and a y. If I'm only giving you an x, you got to find the y yourself. Where do you find your y? Who can tell you what your y value will be? F of x. So remember, y equals f of x. Just like m equals f prime of x. So go ahead and for a, now find out the slope and then use that, find your point of tangency with the function, and then write the equation of your tangent line. And that's not your y coordinate. I think you used your slope to find the y coordinate. There it is. Good, good. And then you went ahead and did it in slope-intercept form, so now I have to think. Just fair, but I don't like thinking. All right, so a quantity x minus 1 is 8x minus 8 at 2. Yes. What's the slope of the tangent line when x equals 1? Wait a minute. What's the x coordinate? 1. Oh, that is a 1. I thought I saw a 3. It's Wednesdays. I forgot we're out of time. Clean up our toys. It's y minus 1 equals a quantity x minus
Y minus
y minus 2. Sorry, y minus 2 equals a quantity x minus 1. Sorry, I lost track of time. I thought we had like another 5 or 10 minutes. I don't know why. Please clean up our toys. Who's got my eraser bit?